All right, today we're going to be looking at topics 1.13 and 1.14. And the key idea is function models and selection and construction. So for 1.13, we're going to go through constant first differences, second differences, and nth differences, which we kind of looked at this last lesson, where how we're trying to find if it's a linear, quadratic, or a different degree polynomial based on the table. And we're gonna learn turning point and end behavior clues and state domain and range restrictions and identify assumptions and limitations. As for 1.14, we're going to build models from restrictions, build models from transformations, and piecewise define function models, rational models, regression with technology, and apply the model to answer questions. All right, let's go straight into 1.13. So we have to check the finite differences. And what finite differences means is basically the x's have to be equally spaced out. Like, look at this table right here. There's a difference of one. There's a difference of one. There's a difference of one, right? So you can see that it's 0, 1, 2, 3, 4, 5. It's increasing by one each time. So, okay, our x is good. Now we can look at our y. So how we find what degree polynomial is by looking at the differences. So the first difference between 5 and 3, the difference is 2. It's increasing by 2, right? And to do that, we just like multiply the term that comes after from the previous term. So 5 minus 3, that's 2. 7 minus 5, that's 2. 9 minus 7, etc. It's all 2, right? And since all of these are the same, the first difference, everything is the same. First div. Then everything is linear. I mean, the graph is linear because all the differences are the same in the first difference. So if it was a second difference, then it's quadratic. If it's a fourth difference, then it's like to the power of 4. Seventh difference, power of 7. So basically, the which difference it is, like first or second or third, directly tells you which degree the polynomial is. Okay, so and then from a graph, this is from a table, right? Table. But if we want to see from a graph, then we can find out through these indications. So if there's one peak or valley and it's symmetrical on both sides, then it's a quadratic. For example, here, this is the peak. This is the one peak, and it's symmetrical on both sides, so it's a quadratic. Another example is like that. Then this is the valley. So it's like the lowest point, and both sides are symmetric. So again, it's a quadratic. And if there's multiple turns, then it's something higher than a quadratic. So that's something like it goes like that. Yeah, it's higher than a quadratic because each time we're intercepting the x-axis has to be like at least one, like if we're each time we're turning is going to be at least 1 degree. So like here is at least 1 degree, here's at least 1 degree. So uh or actually it's one more than that. So like for example, a linear graph 0 turns, so it's going to be degree 1. A quadratic has 1 turn, so it's going to be at least degree 2. But there are examples where like even it's not like you can get that the minimum of turns. So for example, if there's 2 turns, then you know the degree has to be at least 3, but it could also be 4. So like here, there's 1 turn, 2 turn, 3 turn. So actually, this example follows our pattern. Basically, like the degree is going to be one more than the number of terms. And then lastly, we have to state our assumptions, which is domain and range restrictions from the context, and what stays the same, and what are the limits. So I'll show you guys that with some examples. So here's this table, right? Here, I'm gonna scratch this out for now. Okay, so let's look at, first of all, let's check the x increases by 1, 1, 1, 1. Okay, the x seems to be uh equal differences. So now let's look at the y. 3 minus 1. I'm just gonna write down the differences now, right? 3 minus 1, 2, comma, and then 9 minus 3, 6, comma, 10, comma, 14, because 14, 33 minus 19 is 14, 51 minus 33 is 18. So now this is the first difference, right? So I'll write first. Now let's look at the second difference. It's going to be 4, 4, 4. Okay, so all our second differences are the same. So therefore, this is going to be degree 2, which is quadratic. And as you can see, if we actually put these points in, it goes something like that. And it is, in fact, a quadratic function. Now here's a second example. A graph crosses the x-axis 3 times and has 2 turning points. So since it has 3 zeros, 2 turns, remember our polynomial has to be at least 1 degree greater than the number of turns we have. So if we have 2 turns, then it has to be at least degree 3. So just looking at this graph, I'm gonna continue it. This goes like, okay, it passes through the 0. This is degree 1, and it passes through, but ends here. Remember earlier in the unit, I think it was one of the first couple lessons, we looked at how graphs, when it passes through zeros, if it goes straight through it, then it's the 0 has a degree of 1, a multiplicity of 1. So for example, let's say this point is -3, then this would just be x plus 3. But if you look at this point, it doesn't go straight through it. It bounces back. And when it bounces back, it's actually going to be a quadratic, which or quadratic is the lowest possible. It could also technically be quartic, which is degree of fourth. So let's say this point is 2. Then this is going to be x minus 2, let's say squared. So that's going to bounce. So lowest possible, therefore we've proved that the lowest possible degree this could be is 3, because this is going straight through. Here it's bouncing. And it could also be greater because this could have been x minus 2 to the fourth, and it still bounces back. Like, and since they haven't given us specific points, we can't tell, but we can tell that the lowest possible degree is going to be 3, because x times x squared, it's going to be x cubed. So that's going to be our lowest possible degree. Now, all right. So I have 2 problems for you guys here. So problem 1, determine the model type for this data, and then state one assumption that you would need to make to get the model type. And for the second one, a ball is thrown upwards and its height rises, then falls symmetrically. What function type models this? And then state the domain and range restrictions for this context. And for the range specifically, you don't need to give me specific numbers for the maximum, but you can give me the context if you understand what I'm saying. All right, I'm gonna go ahead and solve these 2 questions in 3, 2, 1. Okay. So first problem 1. So first thing we gotta check is are x intervals equal? So 1, 1, 1, 1. Okay, they're equal. So that checks out. Now we can go straight to the y, and let's look at the first difference. So y, and then first difference. So 8 minus 5, 3, 11 minus 5, 3, 14 minus 11, 3, 17 minus 14, also 3. So therefore, the first differences are all completely equal. So therefore, the graph is going to be linear. Linear. And one assumption that you would need to make technically is if this graph were to continue, we have to assume that it follows the same pattern. For example, what if the graph was like something like this? It's just going linear and then it just does something else, right? Like then it's different, but that's just one assumption. But don't worry, that's not going to be something that they're gonna try to trick you with in pre-cal, but it's just one thing that like we assume a lot of things when we're solving these problems, and that's one that it's nice to point out to know. All right, and then for the second problem, a ball is thrown upward. Its height rises, then falls symmetrically. What function set models this? Okay, so if I threw a ball, right? Let's say this is me. I threw a ball, then the ball is gonna go up. It's gonna reach its maximum, and then gravity's eventually gonna pull it down, and it's gonna hit the floor, and that's it. So if we have one maximum point, or the term we used earlier was like uh for if it was the opposite, it would be a valley, and this it's like a hill, then it has to be a quadratic because we're going down. The gravity on both sides is equal, so therefore it's symmetric on both sides, the rate at which we're falling. So this is going to be a quadratic function. And as for the domain and range, I'm just going to write quad since it takes a long time to write on the screen. And as for the domain and range, the domain is going to be 0 because let's assume that when time equals 0 seconds, that's when I'm throwing the ball, right? So 0 because time can't be negative. And uh the maximum of the domain is going to be when the ball lands. And we don't know when it lands, so we're just going to write that down. When, and it, like I said earlier, like this is what we don't have number values for this, so we just ball lands inclusive. And then as for the range, it's going to be the h thrown. So I'm going to say that stands for the height from which it's thrown, which is like my arm, right? This is going to be that, or actually, no, it's going to be, the range is going to be, here, scratch that out. The range is going to be 0 to the maximum height the ball goes. So max h of ball. So, which is also going to be the vertex of the quadratic function. So goes up and down. And like an actual function, it would probably look something like this. And obviously we could connect it on this side as well, but time can't be negative, so we ignore that. Ignore workspace. All right, and with that, we're done with topic 1.13. And now we're gonna go to 1.14. So we're going to build graphs from restrictions and use the context that the problem gives us to create it. And we're going to build them from transformations, and we're going to start looking at rational and inverse models as well. So here's a model, for example. A phone plan charges $2 a minute for the first 3 minutes, right? And that's just linear. So it's going to be like 3, and let's say like 6, 4, 2. So by minute 1, let's say this is like minute 1, it's going to charge $2, then $4 at minute 2, then $6 total at minute 3 since it's increasing by 2. And after minute 3, minute 4, and so forth, it's just a $6 fee. So let's increase this graph. 12, $6 fee, and then it's not increasing after that. So it just goes like this. And that's demonstrated by this graph right here. So this would be like 3,6. No, sorry, 3,12. No. Yeah, 3,12. Then it just increases. All right. Here's our given conditionals. A rectangle has perimeter 20 meters. Let x equal one side. Okay, so one side is going to be x. And the other side is going to be, so we know that if one side is x, then 2 times x plus the other two sides, which we can denote by, let's just use 10 minus x because the perimeter gets 10 minus x. So it's going to be 5 and 10 are the two perimeters. Then a of x equals, then for the area, it's going to be a equals x times 10 minus x. And as you can see here, it's negative x squared plus 10x. Max area at the vertex is going to be x equals 5 when the area is 25. And that's just from using this graph, right? Because we're going to get negative, and then we can just factor like negative x minus 10 minus x. Then we're going to have a point at 0 and a point at 10. So halfway is going to be where our quadratic vertex is, which is 5. We plug in 5, we get 25. And that question was kind of worded weird, so like don't take too much from that one. And then this one's gonna should be a little better. Okay, 12 workers split a task equally. So if there was X amount of workers, so X workers, and the Y depends on the number of workers. So Y is gonna be the time each worker spends, which gets reduced as there's more workers. Each worker spends. And therefore, y equals 12 over x. And that's going to be how we model our graph here. And this will give us the number, the time each worker spends, which is the y-axis. Time, I'm not going to write that down again. I'm just write time. And then number workers. So for the number of workers, the time it gets, this graph will show us. So let's give you guys some example. Yeah. Yeah, I think these questions, let me just check if they're looking good. Okay, that looks pretty good. Yeah. All right, yeah, both these questions look fine. So I'm gonna have you guys go for solving these questions now and let me know if you need any help. All right, so I'm gonna go ahead and solve these problems in 3, 2, 1. Okay, so parking garage. Let's just for problem one, how we're gonna approach it is first let's draw out the graph with the points that we have given. Okay, so parking garage charges $4 for the first hour. So okay, first hour, 1, and this is gonna be 4. So okay, we start at 4. Obviously at 0 hours, it's gonna be 0. So you have that. Next, $2 for each extra hour. Okay, so and remember, this is key, up to a daily max of $14. So it's gonna increase by 2 until this reaches 14. And since the 14 is 10 away from this, I can quickly tell that it's gonna be 5 more. So 1, 2, 3, 4, 5. So let's say that this is 14. Might not be perfectly to scale, but this is going to be like here. So here, okay, so let's try this. It's the rate of change from 1 to 6 is going to be 2x. And then it says the daily max is 14. So it's just going to be that. Oh, and actually, Danya, I apologize for earlier. You were correct. The domain would be a max of 24 since the day is 24, and then it doesn't go after that. So this goes until 24, 24, and then it just reset since the day would have restarted. So I do apologize for that. You're correct. And okay, so that is 2x, the slope is 2x. Here, the slope is just 0. You can ignore that. This, it's X. And how to actually write a model for this is going to be writing different, no, this is going to be 4X, sorry. Is going to be writing the different like rates of change across different portions of the graph. So it's going to be 4X, Y equals 4X for from 0 to 1. So 0, comma 1. And then here, I'm gonna write the rest down. Y equals 2X from 1 to 6. It's gonna be a domain. And then Y, it's just Y equals 14. Actually, over here for this, let's write 2X plus 2. That way we get our exact actual linear line. And then Y equals 14 for X is X from X equals 6 to 24. It's going to be Y equals 14. So that's our answers for problem 1. And then problem 2. Okay, first of all, a person can print 600 pages. The number of pages per person, no, a printer can print 600 pages. The number of pages per person when shared among X people is 600 divided by X. Okay, pretty straightforward. The domain restriction. Okay, so there could be like the people could keep increasing to infinity. So I think our greatest could be infinity. And as for our least, people can't be negative. So the least amount of people you could have is 0. And so we write that 0. But something key here, I didn't include the line that means 0 is inclusive because X cannot actually be 0 because then 600 divided by 0, that would be undefined. So our domain is going to be 0 to X to infinity. Or also, I made a mistake here. There shouldn't be a line there either because infinity can never be inclusive. Okay, making a lot of mistakes today. Okay, find P of 5 and interpret it. Okay, so P of 5, we just plug in P of 5, we plug in 5 for X, so equals 600 divided by 5, which is similar to 60 divided by 5, which is just 120. Okay, so it's going to be 120. And then interpretation for this is the X is going to be the number of people and the Y is going to be the number of pages, right? So the interpretation for this is here. Let me write a text box. For when there are 5 people sharing the printer, there will be 120 pages per person. Shoot this way. Okay, nice. Now describe the end behavior and what it means in this context. So the end behavior is going to be when there's like a large amount of people. So as the number of people increase indefinitely until infinity, right? They just keep increasing. The number of printer pages per person will decrease indefinitely as well, approaching 0. So what that actually means, let me move this up so it's not covered by that. So as there are more and more people using the printer, the number of pages is going to decrease. The number of pages being used is going to be shared per person is going to be decrease, 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 and it's going to keep being decreased, but it can never actually be 0 because even like take a huge number, like if there was a billion people, there would still be like a sliver of a paper per person. So it wouldn't actually be 0. So therefore, uh, it'll approach zero, but it will never actually reach zero. So now let's put together the concepts we learned today with this problem. So first thing they're going to ask for is do finite differences, which remember is the x, suggest a polynomial, and then y or y not. And then the data levels off near 8.5 grams. A rational growth model is proposed. 8.5 t over t plus 1. Find m of 4, the horizontal asymptote, and interpret both in context. Okay, so the data levels off near 8.5 grams, right? So because of that, this rational growth model, I don't know what they're asking you there. They're asking you if it's valid. Ignore part B, and then for part C, just find M of 4 and the horizontal asymptote, and then what they both mean. And then that's gonna probably be it once you guys solve that.